Okay, so this is the explanation of the simulation station. Let's open it. Okay, this is the interface, and we have in this part we have the number of points, number of paths, and the histogram position we can choose. In this box we have 5 different models which we can simulate, and a button to generate them. So, for example, let's start with the geometric Brownian motion. Let's put 10 and number of paths. Okay. So this is the Brownian motion plot. We can observe that in this box we have some information. So, like the mean, variance, the starting point that is 30, and we can observe also this line that indicates the starting point. The number of the intervals for the histogram distribution, and the range of x and y. Okay, so we can see that all values are in, in this part. We have that almost all values are staying are not too far from the starting point. In fact, we can see the distribution that is mostly concentrated in the center values. When we increase the time, the histogram position, so we, for example, let's take 50, we can see that the distribution changes, and we have more concentration in this part, in this region, above the starting point, rather than this region. In fact, if we increase more, like 150, we have that the concentration in this region is so negligible that is not very understandable in this histogram. These are the intervals and the rectangles that show us the frequency, but they are very, very little. And in this region, the situation is different, and we have that values are mostly concentrated in this part of this area of the plot, so very, very near from the zero. If we compare to the last histogram, the situation is almost the same. There are just more values concentrated in this region and less concentrated in this region. Okay, so let's move to the standard, to the Vasicek model. Okay, let's start with 10 and the histogram. Let's start with the value and a good number of paths. Okay. In the plot information, we have a Vasicek model with mean 9, variance 10, a speed of relation of 0.1, the number of subintervals are the same, and the starting point is 15. We can observe that near from the starting point, the distribution is looks like a normal, but is moved up in the x-axis. When we increase in time, for example, let's take 50, we can observe that the normal is now stabilized in in this mean, and continues to be in this mean, since the plots also are stabilizing in this mean. They are all starting. They all starting from the starting point that is 15, and they then they stabilize into 9 that I set here. So we can just see that if we increase in time, it remains stabilized in mean. Okay, we can move to the standard Brownian motion. Let's take less number of paths just to quickly refresh the plot when we change histograms. Okay. Okay, we can see that the Brownian motion, in the Brownian motion, okay, I think it's better with 100. Okay, Brownian motion, all value are yet concentrated yet around the mean, so the distribution looks like a normal. And when we increase in time, since the variance increases in time, we can observe that this distribution is toned down. This curve at the end will not be a very curve. In fact, this is because the variance is becoming larger and larger, because all different paths are going far from the mean, that is 0. So let's increase time. Okay, we can just observe that the situation is different. We have a normal, but is toned down a lot. And if we increase more, we can barely see the normal. Okay, so if we compare to the last histogram, the situation is almost the same. That this histogram has a variance that is greater than this, but the situation is almost the same. Okay, now let's plot the Poisson with lambda. This Poisson is a stochastic process where we used to memorize the previous step of for each plot. We memorize the previous step, pure random step. The random step is obtained by the function that returns 1 or 0 if in the case of success or failure. So if we select this one. Okay, so this is our stochastic process, and we can see at 10 we cannot see a normal distribution, so we have to increase with the histogram position to start to see a normal. Okay, and this is because the values are concentrated, are not very distant from the center line. So since with time they tend to go far, we can see that the variance is increases. In fact, we are starting to have frequency in new regions, and so the final result is looks like a normal distribution. Okay, let's move on the Bernoulli simulation. So we have 1000 number of points and 300 path. We can start and no. Okay, let's generate our Bernoulli. Okay, so this was to demonstrate the law of large numbers. In fact, we can see that now here we have that we have yet values that are outside the epsilon strip. Epsilon strip is this interval, and the center line is the population mean. So we have that if we increase in time, okay, we start to have that all the frequency greater than zero are always here. But we have example to choose a good position to understand better. Okay, okay. So for example, in this time, the time 450, we have that all paths are staying inside this strip. So the probability of having any path outside this strip is equal to 0. And it goes on like this and continues in the same behavior. And the final histogram is only have only the almost the center intervals, because when increasing time they are approaching the population mean. So if we go more and more, they are approaching more and more the population mean, so they are more accurate. So this is the explanation of my simulation station.